Okay, so this is radioactivity. Now, radioactivity is essentially if you have something that is radioactive, it will be a material, okay? And this could be radioactive. And if it is, you usually get that, the nuclear symbol. Sorry, this would be a real poor drawing of a nuclear symbol, okay? Showing that this thing is radioactive. Now, radioactive stuff gives off radiation. Now, radiation can just be light, okay, electromagnetic waves, or it could be a particle. Now, radioactive stuff that we are looking at for nuclear gives off three things: alpha, beta, and gamma, okay? And alpha and beta are just particles in a particle sense, and gamma is just electromagnetic radiation. So, radioactivity is the emission of particles raised from nucleus unstable atoms. The emission is spontaneous and random. Okay, happens by itself. You cannot look at a particle as radioactive material and change when it's going to be released. Okay, random. It just happens with a certain predictable average. Okay, and you can't change it. Now, there is background radiation around us all the time. If you have a look at if you have a brick wall in your house and so on, then you can get radiation from that. You can get radiation from the sun and so on. There are three types of radiation: alpha, beta, gamma, and these can be detected using the Geiger Miller tube. Okay. So what happens here? As some radiation comes flying in from the outside, okay, there is a gas on the inside, and this gas will become ionized, in other words, charged. And let's say if it was turns into, let's say, a negative charge, okay, so there's a negative charged atom in there, then that will head towards the positive anode, okay, or if it was a positive charge created, then it will head towards the cathode, and that will actually create some sort of current. So if you could actually measure a small current flow, then, the other way, then you would actually be able to measure how many things are going inside the tube, okay. So you'll see, like in your ammeter, you'll see a little blip, 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 as the particles come in. What are the characteristics of the radiation? Okay, so alpha is just a helium nucleus, okay? Nothing special about it, just helium. It's got no electrons around the outside though, that's why it's 2+. Why is it dangerous? In the sense most radiation is dangerous, is because it travels quite fast, okay? So it has high kinetic energy. It's highly ionization, okay, due to frequent collisions with the air molecules. So as it flies through, it can see a molecule, and it can take off an electron. So there's a little electron around the outside. As this thing comes in, it will take the electron with it, and the thing will become charged. And that's effectively a collision. And every time it does that, it will lose energy. And because it's so big and so highly charged, it will hit a lot of things, and it will slow down very rapidly. And that's why it only travels up to a few centimeters in air, or you can stop it by a thin sheet of paper. So if we had a thin sheet of paper, fired alpha at it, it will get stuck on it, okay, when it gets through it. Beta particles are high energy electrons. They're just electrons, but they have high kinetic energy because they're going so fast. They're not as ionizing as the alpha particles because they're small, not as charged, so they can get through more. They can travel several meters in air, and they're stopped by a few millimeters of aluminium. So we have paper here and aluminium, okay. Then the beta will go through the paper, but won't get through the aluminium. And the last one is gamma rays. A high energy electromagnetic radiation travel at the speed of light, less ionizing than beta particles. They're high frequency, and that's why they're high energy. They hit the rate is probably, in terms of the speed, is the same as all electromagnetic radiation, it's the speed of light, but because the frequency is higher, there's more energy dropped off per second. Less ionizing the beta particles, mainly because they're so small, they can go through things. You've got your atoms. Okay, generally it'll just go straight through, won't see anything. Stopped only by many centimeters of lead. Okay, and so we need a whole lot of lead. PB, okay, small b, to stop it. And so that will come right through all that and then get stopped by that few centimeters of lead. Which one is the most dangerous for humans? Probably something like the alpha or beta, depending on where they are. If you swallow alpha, well, it definitely hits your skin or hits your interior of your body. So that's what makes it dangerous. Gamma, you could swallow something and have that releases gamma radiation, but a lot of the radiation will actually escape your body. Okay, so that's why alpha and beta are the most dangerous. Passage through electromagnetic fields. Well, alpha, actually both of these, what goes straight? Well, one thing is uncharged, and that's gamma. Gamma goes straight through both of them. Now, which one curves towards positive, and which one curves towards negative? And which one curves this way on that one, and this way on that one, making sure that these are circles and these are parabolic. So, the answer here as well. The helium nucleus is positively charged, the alpha is positive, so that must go towards the negative. And the electron, the beta, goes towards positive. And then the other one, you have to do left-hand Fleming's, okay? And you can find that this one here is your alpha, and this one is your beta. Remember, the current is in the same direction as the positive charge. Alpha is the direction of the current, while beta is opposing the current. And the second last thing, radioactive decay. Okay, so radioactive decay is where you have some radon, radium there, and it turns into radon, and it releases a helium nucleus, okay, or alpha. Important thing you have to remember for these is that you just balance the equation. So there's 226 on the top here. The total on this side must also be 226. The bottom's 88. Then the bottom on this side must also be 88. And that happens for beta. There's 14 there, and it must be 14 there. And there's 6 there, and it must be 6 there. Now, you must wonder, why is the proton number -1? That's because the actual beta particle comes from the nucleus. So here's our nucleus. There's protons, neutrons, proton, neutron, proton. Okay? Now what happens is your neutron splits into an electron that leaves behind a proton. So we have just gone from 3 protons to 4, but still keeping the same total number of nucleons. Okay, we've had 2 neutrons and we've gone to 1 neutron, but in total is 5 before and after. So our mass number up here has stayed the same at 14 and 14. However, our proton number has gained because we've gained that extra proton. Half-life. The rate of decay is not affected by temperature, but every radioactive element has its own decay rate expressed by half-life. So the time for half the atoms of a given sample to decay. In other words, you might have 10 kgs of butter, and after 5 years, it might turn into be 5 kgs of butter and 5 kgs of margarine. So after half that time, there's a certain time for half of the stuff to change to something else. So the half-life for radium is 1,600 years. The activity of the sample of radium is that. Complete the table showing the number of disintegrations per second. So in other words, 320 at the start. So let's have a look. 320, time is 0. After the first half-life, okay, which is 1,600 years, the activity would halve. So 160 disintegrations per second. Then the next half-life, 3,200 years, okay, and it will halve again, okay, so you get down to 80, then you go 40, 20, 10, and so on. And what you'll find will be a curve that you should plot, okay? And so there's your original time equals 0, and you'll find that there will be some sort of half-life where it's got down to half the amount. And this is the time here.